here, guess what that's going to trigger? Oh, voltage-gated sodium and potassium channels are going to open here, and you're going to get it here. Guess what that's going to trigger as soon as that happens? Oh, voltage-gated sodium and potassium channels right here are going to open, and you're going to get it right here. Guess what that's going to trigger? Voltage-gated sodium. So all along here, this is going to spread. So the way to think about it is that you depolarize toward the axon terminals, and you repolarize back towards the hillock. So depolarizing to the front, repolarizing to the rear. So if I'm an axon down through here, depolarize, repolarize, depolarize, repolarize, depolarize, repolarize. So this just keeps continuing as long as there are voltage-gated sodium and potassium channels. And the end of the road is what? The axon terminal. So an action potential will spread from a hillock to a terminal because there are adjacent voltage-gated sodium and potassium channels all along through there. It's like a domino effect. Once one happens, the next one happens. The next one happens, the next one happens, the next one happens, the next one happens. So we let them fall to the front, and then we set them back up behind it. Let them fall to the front, set them back up behind it. Okay? So we get this, it's called a wave, of depolarization, because what's happening is that there's an action potential spike right there, which causes one right there, which causes one right there, which causes one right there. So this wave spreads to the front, depolarizing to the front all the way to the terminals. Okay? What caused it? Ion flux. Sodium influx precedes potassium efflux. And then sodium-potassium pumps reset. Sodium influx, potassium efflux, reset. Sodium influx, potassium efflux, reset. Sodium influx, potassium efflux, reset. All the way down through until eventually where this is going, right, is something like this. And an action potential right here will give you an action potential right there. Okay. And then guess what that action potential causes? Release a neurotransmitter. Okay. Now, and which we'll get to in a second, the only thing I want to just briefly mention here is that in order for that action potential to spread, we need to exchange ions. Right? And we exchange ions by opening channels, closing channels, and whatever. The only thing that's a little bit confusing in this, and I don't want to spend a lot of time talking about it, but is that if we want it to go faster, we do that by adding myelin, right? Schwann cells, right? Myelin sheaths, or this could be oligodendrocytes in the CNS, like that. So where are action potentials generated? They can't be generated here, because this is insulated, right? It doesn't allow for an exchange. They're actually generated here. So you get an action potential there, and then it whizzes through there real quickly. And then you get another action potential here, and then it whizzes through there real quickly, and you get another action potential here. So in myelinated axons, where this action potential gets regenerated, are on the nodes of RANVA. Now it's a little confusing about why it moves faster here, but remember I told you before that diffusion occurs faster than active transport and whatever. The reason that it moves quickly through here is because there's a whole lot of ion flux right here that pushes it through there really quickly. And this is just lowering resistance. So we won't worry too much. It's called cable properties and stuff like that, and you know, it's not really worthy of the discussion. We used to call this, well, they still call this saltatory conduction. Saltatory means to jump. Like it jumps from node to node. That's misleading because nothing is coming out of the membrane. In fact, it goes through here. So it's more like this. It's like action potential. Shoom. Just like it just gets regenerated at every point along the way. It's another boost and just pushes through. And it makes it go through real fast. So without getting into the physics of it, can the speed with which an action potential moves change? Sure, we talked about it before. If you wanted to have action potentials move fast, you add myelin, and you make them have a large diameter. Okay, that's all. Okay. There. If it can move slow, you have no myelin, and they can be a small diameter. And this will affect not how many action potentials you get, but the speed with which they can move. You can get from hillock to terminal faster here than you can do here. To give you an idea, this can be as fast as 280 meters per second. Do you think that's very fast? Yeah, that's over 300 miles an hour probably. So the largest diameter axons with myelin would move 280 meters per second. The smallest diameter axons we have that are unmyelinated in the body, it's about 1 meter per second. We have this obviously over short distances, this over long distance, because speed is important for us, right? So what we need, the discussion we need to have after we take a little break is, okay, what happens right here? What happens when that action potential reaches that terminal? How does it trigger the release of the neurotransmitter? Then the discussion to have is, okay, what kind of neurotransmitters are there? What are some of the responses that they can give in a general sense? And then we'll look at specifically, how does this information, is it altered at all in the way information flows in the autonomic nervous system versus the somatic? Okay? You all right? Ready for a break?